Today we're jumping into a really fascinating paradox in modern AI. You see these models getting incredibly powerful, right? They write code, make amazing art, they can even reason in complex ways.
Absolutely phenomenal progress.
But the flip side is that every step forward seems to come with this just astronomical price tag.
Right.
So have you ever wondered, how does AI keep getting smarter without becoming totally unaffordable for almost everyone? Or maybe why the really cutting-edge stuff seems to only come from like a handful of tech giants? Our mission today in this deep dive is to unpack two really groundbreaking approaches that are starting to break through this sort of unseen wall. We're talking mixture of experts MoE and the newer idea, mixture of agents, or MoA.
And it's important to stress these aren't just, small tweaks. They really represent a fundamental shift. We're moving away from this idea of one giant monolithic brain.
Towards what, like specialization?
Exactly. Specialization and collaboration between different parts or even different models. Yeah.
Because the traditional way, these dense monolithic models, they ran into what you could call the tyranny of scale. Picture trying to answer one simple question. But to do it, every single person in a giant library has to read every single book on every shelf all at once. That's basically a dense model, right? Every single parameter, every connection is activated for every piece of input. It sounds simple maybe, but as the models got bigger and bigger,
it just became catastrophically inefficient.
So inefficiency, what did that actually look like? What were the real pain points?
Well, it boiled down to three critical things that just became impossible to ignore. First, the sheer cost. Training GPT-3 back in 2020, estimates were like $500,000 to maybe $4.6 million. Just a few years later, GPT-4, reportedly over $100 million, with compute alone estimated around $78 million.
$100 million.
And Google's Gemini Ultra, the estimate there is maybe $191 million just for the compute needed for training. And these aren't just numbers, right? That represents running thousands of super high-end GPUs continuously for months. It creates this massive barrier to entry.
So it really is just a handful of players who can even afford to build these foundational models from scratch.
And that financial cost, it's really just a proxy for the second pain point. The astronomical computational requirements. We measure it in FLOP's floating point operations. Just getting an answer from a huge dense model, what we call inference, demands this immense number of calculations. Think about GPT-4 again. Training took something like 2.1 times 10 to the 25th FLOPs. And that massive compute need makes using the model inference really slow and expensive too. Often, it makes deploying it at scale just economically unviable, especially if you need quick responses.
What was the third one?
The third pain point is a bit more subtle. It's what we could call the knowledge encoding dilemma. A single monolithic model has to learn everything, right? It's trying to be a master of Shakespeare and Python programming and medical diagnosis, all using the same shared set of parameters.
Like a jack of all trades.
And that leads to this issue sometimes called knowledge hybridity. The knowledge for one area can kind of dilute or even interfere with knowledge for another area. It's just really hard to achieve deep mastery in specialized domains when everything is crammed together.
Right. Trying to be good at everything means you might not be truly great at any one specific thing. The solution you mentioned earlier was conditional computation. This idea of only activating the relevant parts. You use the analogy of a scholar going to the right shelf in the library, not reading the whole thing.
That's the core idea. Instead of activating everything, you only compute the parts of the model that are relevant to the specific input or task at hand.
But I imagine making that work in practice wasn't straightforward. What were the hurdles?
The fundamental benefit is you can dramatically increase the total knowledge or capacity of the model.
More parameters, more potential knowledge.
Super linear increase in capacity, but without a proportional increase in the computational cost for each inference, because you're only using a fraction of the model each time. The compute path changes dynamically. And what's really fascinating is that mixture of experts, MoE, which is built entirely on this conditional computation idea, it actually dates back to the 1990s.
The 90s. But it kind of languished. It only really took off when the economic pain of scaling dense models like GPT-3 became so acute that pressure made finding a more efficient approach absolutely necessary. It went from being this like academic curiosity to a practical necessity.
Tell us more about MoE Mixture of Experts. How did it start and why did it take nearly 30 years to make a comeback?
So MoE first popped up conceptually around 1988 and then was formalized in papers around 1991 by researchers like Jacobs and Hinton. The basic concept was divide and conquer. You have a set of smaller neural networks. These are your experts, each designed to become a specialist. And then you have another network called the gating network.
And the gating network does what? Writes the traffic?
It looks at the input and decides which expert, or maybe which few experts, are best suited to handle it. Early versions even use competitive mechanisms to force the experts to specialize, kind of fight over who got to learn from which data. So why didn't it take off back then? What held it back?
Well, there were several pretty big roadblocks. First, training these things was notoriously unstable. Those early gating mechanisms, especially the competitive ones, were hard to train well. You'd often get a situation where one or two experts became overpowering, grabbing all the useful training data, while others were effectively starved and never learned much. Second, just the implementation complexity. The hardware and software back in the 90s just weren't built for this kind of dynamic routing. It was awkward. And the real killer was something called the shrinking batch problem. Think about it. If your main input batch gets split up, with different inputs going to different experts, each individual expert ends up processing a much smaller batch of data.
And why that bet?
Because modern hardware, especially GPUs and TPUs, they thrive on parallelism. They're designed to crunch through large batches of data all at once. Processing lots of tiny batches is incredibly inefficient.
It completely negates the potential computational savings.
It wiped out the theoretical benefits. It was like, having a Ferrari but only being able to drive it in traffic jams. You just couldn't use the power efficiently.
So fast forward to 2017. You mentioned Google Brain had a breakthrough. How did they finally get that Ferrari out of the traffic jam?
That 2017 paper was a game changer. They systematically tackled those old problems. Key innovation. They introduced a sparsely gated layer. It used a soft, differentiable gating network. So it calculates scores for all experts, but then uses a clever function like a top K selector. Maybe pick the top 2 experts, for instance.
K equals 2.
Only those top K experts actually process the input, and then their outputs are combined, usually weighted by the gating scores.
So it's still sparse, only a few experts work, but the selection is smoother.
And they added other tricks like noisy gating, which introduces a bit of randomness to help balance the load across experts over time.
Preventing the starvation problem.
And crucially, they added an auxiliary loss function. This is a separate penalty term during training that explicitly discourages the gating network from always picking the same few experts. It forces more balanced routing.
That sounds like a really key piece.
It was huge for making training stable and reliable. But the other half of the breakthrough was just as important. They paired these algorithmic improvements with hardware-aware system design, meaning they figured out how to combine techniques like data parallelism and model parallelism in clever ways. This ensured that even though the activation was sparse, each active expert still received a large, efficiently processed batch of tokens on the modern hardware. That combination unlocked the door. Suddenly, MoE was practical and efficient on modern GPUs and TPUs. It paved the way for trillion-parameter models. And this is the tech that powers huge systems like Google's G-Shard and Switch Transformer. It's also what's inside popular open-source models like Mistral AI's Mixtral 8x7b.
The Mixtral model, right?
It has 8 experts, but only activates 2 for any given token. So it computes roughly like a 14 billion parameter dense model, but actually holds about 47 billion parameters in total. More knowledge, less compute per step. And it's very widely rumored to be a key part of how GPT-4 achieves its scale, too.
MoE solves the scaling efficiency problem. But then just recently, this other idea pops up, mixture of agents, MoA. This feels like another leap. Where does MoA fit in?
MoA really emerged in early 2024, and it was driven by a slightly different but equally important development in the AI landscape. The widespread availability of these incredibly powerful pre-trained foundation models, think GPT-4, Claude, Llama, Gemini. Suddenly, lots of people had access to really capable AI brains off the shelf.
You don't have to build your own giant model anymore. You can use existing ones via APIs.
So the focus for many researchers and developers shifted. Instead of figuring out how to build one even bigger model, the question became, how can we combine these existing powerful models in smart ways to achieve even better results?
So MoE is about building a better single model efficiently, while MoA is about combining multiple existing models.
MoE scales knowledge efficiently within a model. MoA aims to improve the quality of complex, multi-step reasoning by leveraging several distinct models working together.
So how does MoA actually work? Is it like MoE with bigger experts?
Conceptually, maybe, but technically it's quite different. MoE is what we'd call an intermodel architecture. It uses entire pre-trained LLMs as the agents.
The whole model is an agent.
And it sets them up in a multi-layer collaborative system. Think of it like a really productive team meeting or brainstorming session. You might have some LLMs act as proposer agents. You give them a complex prompt, and they each generate different initial ideas, different drafts, different potential solutions. Then you might have other LLMs act as aggregator agents or maybe critique agents. Their job is to look at all those initial proposals, synthesize the best parts, critique the weaknesses, and refine everything into a final, hopefully superior answer.
Leveraging the idea that LLMs get better when they see examples, including examples from other LLMs.
There's this fascinating finding that showing an LLM the outputs of its peers often prompts it to generate a much better, more refined response itself. MoE operationalizes the finding.
MoE is like tinkering with the circuitry inside one brain.
Right, optimizing the connections.
And MoE is like orchestrating a conversation between a whole council of brains.
And it's not just theoretical, it's already showing real impact. An open source MoE framework from Together AI actually outperformed GPT-4o on a benchmark called Alpaca Eval 2.0 earlier this year. It shows the power of collaboration.
Okay, so this brings us to the practical side. If you're like me, maybe you're a developer, a startup founder, someone trying to build things with AI, but you definitely don't have that spare $191 million lying around for training. What does all this mean for you? How do you decide between MoE and MoA, or when to even think about them? It feels like a classic build versus buy kind of decision, maybe, or build versus lease.
Build versus buy or lease, with some AI-specific nuances. Let's compare them directly across a few key areas. Understanding the trade-offs is, well, crucial. First dimension, architectural level. We touched on this, but MoE is intramodel. It's a technique you build inside a single neural network, often replacing standard layers like the feed chord blocks.
Inside the model.
Right. MoA is intermodel. It's a system, a framework built around multiple independent, usually pre-trained models. It orchestrates how they talk to each other. Second, granularity of expertise. With MoE, the experts are typically quite small subnetworks. They become highly specialized, but on fine-grained, low-level patterns, recognizing specific visual features or maybe subtle grammar rules. With MoE, the experts, the agents, are coarse-grained. They are entire, powerful LLMs, each potentially having broad capabilities. Maybe one is tuned for legal analysis, another for creative writing, etc. Which leads to the primary goal. MoE's main goal is scaling efficiency. How do we pack more knowledge parameters into a model without making inference prohibitively expensive? It's about getting more bang for your compute buck.
More knowledge per dollar.
MoE's primary goal is improving reasoning quality, especially for complex, multi-step tasks where having multiple perspectives, critique, and refinement really helps generate a superior final output. Though MoE quality is also very high. Now, think about the implementation stage. This is a big one. MoE is fundamentally a training time architecture. You decide to build a MoE model before you start the massive, expensive training process. It's baked in from the start. MoA, on the other hand, is usually inference time orchestration. You take existing pre-trained models, maybe ones you get through APIs, and you build the MoE system on top of them. No need for that massive upfront training.
What about speed? Latency is often critical.
Inference speed and latency. This is often the deal breaker. MoE models are designed to be fast. Even though only parts are active, it's typically a single, efficient forward pass through the network. This makes them suitable for real-time stuff. Chatbots, code completion, things that need quick responses. MoA is typically slow, high latency. Why? Because you're often making multiple sequential calls to several large language models over APIs. You send a prompt to the proposers, wait, get results, send those to the aggregator, wait again. It adds up quickly. So MoA is generally unsuitable for most applications needing real-time interaction.
Okay, that's a clear trade-off. Speed for MoE, potentially higher quality but slower for MoA. What about the main challenges for each?
The primary challenge for MoE still lies in the complexity of training and routing. Ensuring stability, preventing expert collapse or starvation, getting that routing balance just right, it requires significant expertise and careful tuning during the build phase. For MoA, the primary challenges are coordination and cost. The operational cost can be high because you're paying for multiple API calls to potentially expensive models for every single query. And designing the workflow, how the agents interact, what prompts you give them, that can be complex. It requires clever system design and prompt engineering. So, navigating this choice, how do you decide? I think it comes into asking yourself three key questions. Question one, what is your primary objective? Is it scaling knowledge efficiently while keeping latency low? If yes, you're looking at needing a MoE-based model, either building one if you have the resources or using an existing one. Is your goal to maximize reasoning quality for really complex, maybe multi-turn tasks where latency isn't the main concern? Then MoE is a powerful technique to consider applying.
Objective first, efficiency speed versus complex reasoning quality.
Question two, what are your available resources? Are you a huge research lab or tech giant with, hundreds of millions in budget, thousands of GPUs, deep ML expertise, ready to train a foundation model from scratch? If so, MoE is a fundamental architectural decision you'll make.
The build path.
Or are you a developer, startup, or researcher wanting to leverage the best existing models available via APIs? In that case, MoE is a much more accessible technique you can use right now to innovate on top of those models. And question three, what are your constraints on latency and cost? Does your application absolutely need real-time or near real-time responses? If yes, you probably need a MoE model speed. MoE is likely too slow. But if your task is asynchronous, maybe generating a complex report overnight, or brainstorming strategic options where taking minutes or even longer is acceptable for a much higher quality result, then the higher latency and potentially higher cost per query of MoE might be perfectly fine.
It really paints the picture. MoE and MoA aren't really fighting each other. They're complementary tools operating at totally different levels.
Exactly.
MoE helps build better, more efficient foundation models, those base layers of intelligence. And MoA helps build better reasoning systems using those foundation models as building blocks.
And, looking towards the future, what's really exciting is the potential synthesis of these two. Think about mixtures of MoE-based agents. Imagine a MoE framework, that sophisticated collaborative structure, but where each individual agent isn't just any pre-trained model, but is itself a highly efficient, knowledge-packed MoE model.
So you get the best of both worlds. The scaling efficiency and knowledge density of MoE inside each agent, plus the high-level reasoning, critique, and refinement capabilities of the MoE structure coordinating them.
You combine the computational efficiency at the agent level with the superior reasoning quality at the system level. That could lead to AI systems far more capable and efficient than what we have today. There's already early research, sometimes called self-MoE, exploring how a single model can simulate this kind of multi-agent reasoning internally, which hints at this direction.
So for everyone listening, thinking about your own work, your own interest, given these incredible advancements in both making models bigger and smarter efficiently with MoE and making systems reason better collaboratively with MoA, what complex problem that you care about could be transformed? How could you tackle it differently by thinking about AI not just as one big brain, but as this potential council of specialized collaborative minds? Thank you for joining us on this deep dive into the world of MoE and MoA architectures. We really hope this breakdown helps you explore these ideas further, maybe apply them,